So here we're going to look at the periodic trends. The real strength of the periodic table is not that it has these families and these groups or this weird shape, but that we can use this weird shape and the properties of the elements that are arranged on the periodic table to predict things that are going to happen. Because Mendeleev again showed us that there are certain repeating patterns, and those are called the periodic trends. And we get that from his periodic law. When atoms are arranged according to, now we know, increasing atomic number instead of increasing atomic mass, but increasing atomic number, there's a regular repeating pattern of the elements' properties. That is, certain properties repeat over and over again. What this means, generally speaking, is that things in a column tend to have one particular property, and things in a row, you can see that property change and shift. The next stuff here on this slide, don't jot down, but basically, with one exception, we'll assume that we're starting at hydrogen. We'll define a property, and then I'm going to describe the periodic table as we go across and as we go down the periodic table. I have it typed up. I recommend you do something like drawing it out on a double arrow, and feel free to abbreviate however you like. We'll start out with some simple ones that are kind of super obvious that you would not use a trend to do. I would not memorize these first few trends. I would not pay attention to the trend because it's more obvious if you just look at the periodic table, but I do it to establish the pattern of how the other ones are going to do, the other ones that are harder to think through or intuitively think about. As a side note, I have learned the definitions of these different properties that we're going to do, and I have learned a couple patterns, and from those patterns I reason out all the others. I do not memorize these things, and I discourage you from doing the same. So starting out, atomic number is simply the number of protons for a neutral atom. It's also the number of electrons. As you go across the periodic table, it increases by 1. And as you go down the periodic table, it simply increases. And here on the side, I'll have graphics of what this looks like or some of the data. And you'll do a lab where you'll actually plot some of this data at some point. Next, for atomic mass or weight, it's simply how heavy it is. As we've said previously, is the sum of the protons and the neutrons. Here, as we go across, it usually goes up, and as we go down, it always goes up. And I apologize that the arrow is over top of the word here. And there are a couple exceptions to this. One of the exceptions that I happen to know that stands out to me is actually split in between rows. But as you go across the third period here, you hit argon and then potassium, calcium, and the masses go 40, 39, 40. As you go across like that, there's a brief little dip there with potassium where the mass goes down. There's another one over here, if I remember correctly, it's tellurium iodine region, where the mass goes down by a couple. It never goes down by a lot, and certainly as you go down the periodic table, the mass always goes up. Number of valence electrons is the number of electrons in the outermost energy level. Ignoring the transition metals here, as we go across, it increases by 1. As we go down, it stays the same. For charge of the ions, the pattern is very similar. The charge is a result of gaining or losing electrons. Again, here we're ignoring the transition metals, but as we go across, it's positive and increasing, and then negative and decreasing. And what I mean by that is it starts out positive, and we increase. We go 1, 2, 3, 4. Then at 4, the sign switches to negative, and then starts decreasing, 4, 3, 2, 1, 0. And so the charge of the ions, 1 plus 2 plus 3 plus 4 plus or minus, minus 3, minus 2, minus 1, 0 as you go across the columns. Which means as you go down a column, they are the same. Now we start to get into the ones that aren't as intuitive, aren't as easy to think about. And this one here is to me, the most important one to memorize, because if you can remember this one, you can logic out the rest. So atomic size or radius is simply the measure of the size of the atom. Usually it's measured from the nucleus to the outermost energy level, and it is an estimate based off of the size of the whole atom, the radius there. And there are different ways to measure the radius, but as long as you're sticking with one method of measurement, this pattern holds no matter which method of measurement you use for all the atoms. atoms. So this one, it's easier to describe the down than it is to describe the across. Down, as you go down, it increases, and that should make sense because as we go down, we're getting more and more rings, more and more shells, orbitals where the electrons are. And so the atom size is going to increase as you go down. Remember, the size of the nucleus has very little effect on the overall size of the atom because the atom is so tiny and the space between the nucleus and the electron rings are so big and empty. However, as you go across the periodic table, you might say, well, it's the same number of rings, so it's going to stay the same. But it doesn't, and it doesn't increase, which is the other gut instinct to say, oh, we're going across, we're adding things, we're adding electrons, we're adding protons, we're probably adding neutrons, it must increase. It does not. As you go across the periodic table, the atomic size actually decreases. So as we go down, it increases. As we go across, it decreases. And this is counterintuitive, but is probably the most important one of these trends to learn. I'll explain in class why in full this happens, but it's easier if you can see it, and I'm not sure that the recording here is the best place for me to emphasize this.
So this is future me discussing this, but I'm going to go ahead and try to explain that here on video. I'm doing that in part because of just the weird situation we have this year with some people remote learning, and it's going to be harder to explain to everyone if I don't try to do it here. So we're going to imagine that these marbles here are electrons, and we're going to imagine that I, in my head, is the nucleus of an atom. And so the nucleus of the atom, of course, has the protons and on occasion, usually when they're there, the neutrons. But we're going to deal with just the first row of the periodic table, hydrogen and helium. And so hydrogen has just one proton in the center and just one electron. Now, obviously, if I do a full orbit here, I'm going to go off the screen, so I'm just going to talk to it out to the side here. But this here is our one electron, and the one electron, of course, does go all the way around the hydrogen atom as it orbits. And that one proton attracts the one electron. Now, as we talked about with the gold foil model, the space in between is empty. And so the electron is attracted to the nucleus, and the only way for it to not be pulled into the nucleus and attracted to that proton, it actually turns out when a proton and electron combine, they form a neutron and would cancel out, and then we'd have nothing but neutrons in the universe, and neutrons don't make anything. And so the only way for that to work is if the electron is moving, and then because it's moving, it's like an orbiting planet, and as it goes around, even though it's being attracted to the nucleus, it's constantly moving around it and is never pulled in. Now, as we go across the periodic table, then we get to helium. Helium has an atomic number 2, so it has 2 protons. Those are both in the nucleus, and it has 2 electrons, and those are both orbiting the nucleus, of course. And by coincidence, it happens to have 2 neutrons, and the neutrons aren't important for this discussion, so we're not going to talk about it. Now, I've already mentioned that as we go across the periodic table, atoms get smaller. But why would it get smaller? We're adding more pieces to the center, we're adding more things to the outside. We remember back when we were drawing Bohr models of atoms that these electrons exist on just one ring of the atom. So they're staying on that ring. And you're like, okay, fine. If that's the case, then why don't we have them stay in the same size as we go across the periodic table? Well, it has to do with those charges. See, down here at the center, there's 2 protons. And it's not like one proton reaches out here and says, I'm going to attract this electron, and the other proton attracts that electron. No, I got to put one of my electrons down here. But both of those protons here at the center grab onto that electron, and they attract it. So this electron feels the pull of not just one proton pulling it in, but 2 protons pulling it in, so it pulls it in closer. And then that other electron, it feels not only the pull of one proton, it feels the pull of both protons as well, and it pulls them in. And so the electric field strength from the nucleus is stronger, and so it attracts those electrons more, and they get pulled in closer and closer. And so then we have those electrons orbiting around closer into the nucleus. Now, I'm going to put those electrons closer than they could actually be because electrons are negatively charged and they're going to repel one another. And so they're going to want to get away from one another as they orbit around the nucleus. But once we have 2 in that first energy level, that first ring is filled up. And so then our next one is way out away from there. Our next electron is way out away in the next energy level. So this is why as you go down the periodic table, as we keep adding energy levels, as you go down further and further on the periodic table, those electrons get further and further away. So that's why the atoms get bigger as you go down. The bigger as you go down is obvious because we're not only adding more pieces, the bigger thing is that most of the space of an atom is those electron rings, and so they're getting further and further away from the center. But within a row, as you go across that row, as you keep adding more electrons, those electrons are all getting added to the outside, but the protons are all getting added into the center. And those protons gang up on those 4 electrons and pull those electrons in closer and closer and closer. So again, as you go down the periodic table, atoms get bigger because we're adding rings, but as you go across, they get smaller because the additional protons are attracting those electrons more and pulling them in, and they feel just a stronger and stronger nuclear charge. So that's your reason why you have that pattern. Now, I mentioned in the video that there's all sorts of other patterns that you could use this one to figure out. That's actually a chemistry topic, so we're not going to cover it here. If you're interested in going deeper, that pattern is the key for understanding all of the other patterns on the periodic table. Anyway, be sure to let me know if you have any questions.